Hello, this is Christian Picofazzi, and this is my presentation on RTS AI problems and techniques. What is an RTS? RTS, or real-time strategy, is a subgenre of strategy games where the players need to build an economy, their military power, in order to defeat their opponents by destroying their base. Artificial intelligence problems is an RTS needs to learn how to play the game, understand it, and the environment while predicting, inferring, and sparsing through the information provided. Some difficulties with RTS AI compared to other games, say Go and chess, are RTS games are simultaneous move games. Actions in the RTS games are derivative, meaning that they take time. RTS games happen in real time. Most RTS games are partially observable, meaning you cannot see the entire state space. Most RTS games are non-deterministic, and their complexity in both space and time is extremely larger than games even like chess and Go. Some early research for RTS AI games have revealed 6 areas of study that have taken the field as of recent time. They include resource management, decision-making under uncertainty, spatial and temporal reasoning, collaboration between multiple AIs, opponent modeling and learning, adversarial real-time planning. There's been significant research in many of these areas. However, collaboration is generally an untouched area of research. Research in collaboration has identified several areas of new challenges, such as how to exploit the massive amounts of existing domain knowledge that there is. So, some challenges when people have been researching and developing AI for RTS games have been planning, learning, uncertainty, spatial and temporal reasoning, domain knowledge exploitation, and task decomposition. Next, we will go through each one of these. Planning. Since the size of the state space and the number of actions that can be performed is so much larger than other games like Go and chess, standard planning approaches like game tree search cannot be utilized to solve an entire RTS game. Planning an RTS game can be broken into multiple levels of abstraction. Higher level, meaning the player's long-term planning goals, like developing a strong economy, and a lower level, which is the coordination of individual units, attacking and defending. Learning. There are 3 types of learning techniques applied for AI and artificial intelligence. One is prior learning, which is exploiting available data like replays, map information, before the game even starts and loading that in. There's in-game learning, which is improving the play while the game is going on, such as reinforcement learning and opponent modeling. And then there's intergame learning, which is using the previous games to aid in its chance of victory, and basically learning from its mistakes. Uncertainty. Adversarial planning under uncertainty is an unsolved challenge in RTS AI. This is because the game is partially observable, as explained before. This can be mitigated through good scouting, but that reduces the amount of economic progress that you could make. There's also uncertainty from the fact that games are adversarial, meaning a player cannot predict the actions that the opponent will make. Sensible models can be built to assume what the opponent will do. Spatial and temporal reasoning. Spatial reasoning, or terrain exploitation, as in building placements and base expansion. But there's also the need for a player to be concerned about their unit placement for bottlenecking and ambushing. Now, temporal reasoning. This is short-term timing attacks and retreats to gain an advantage. And in the long term, this is upgrades and building construction, as in turtling and blitzing strategies. Domain knowledge exploitation. Traditionally, game domain knowledge is used to construct evaluation functions to be used by alpha-beta search algorithms. Since the domain, as discussed before, is so large, there have been 2 different approaches. Hard-coding existing strategies into bots, and mining large data sets of replays. but both of these strategies are shortcuts to get around a much larger domain problem. Task decomposition. Most approaches to RTS AI decompose the problem into smaller pieces. For an AI, the subdivision usually falls under 5 categories. Strategy, or high-level decision processes. Tactics, the implementation of the current strategy. Reactive control, which is the implementation of those tactics. Terrain analysis, which is analyzing the regions composing the map. And intelligence gathering, which is collecting information on the opponent. Now, humans normally divide their RTS games into macro and micro tasks. A macro task is involved with the flow of unit production and expanding the base economy, while micro tasks involve individual unit movements and attacks and defense. Existing RTS work has to be broken down into 3 categories in order to make it relevant to compare to humans. So, as we saw before, the strategy is most closely representing the macro. Tactics are its own branch, and then reactive control is the micromanagement. On the right here, you can see the paper published a little diagram of how each of these strategy, tactics, and reactive control relate and their tasks under them. Also, how frequently they are updated throughout the game process. Now, strategy, or macro. These are some examples of research in this field. There's the hard-coded approach, which most commonly uses finite state machines. And the idea behind finite state machines is that they decompose the AI behavior into easily manageable states. This approach struggles to encode dynamic and adaptive behaviors and is easily exploitable. Next, we have planning. Otano and Co. has explored the use of real-time case-based planning. They use human demonstration to learn plans, which are composed at runtime in order to perform full-fledged strategies. Planning approaches offer more adaptivity of the AI strategy compared to hard-coded. The real-time constraints limit planning and does not address the timing or scheduling issues. Machine learning for strategy. Weber and Mateus have proposed a data mining approach to strategy prediction and performed supervised learning on the labeled replays. Deresnicki used hidden Markov models to learn the transition probabilities of sequences of building construction orders and keep the most probable ones to produce probabilistic behavior models. Now, Young and Hawes used an evolutionary approach to determine the priorities of high-level tasks, which showed improvements over static priorities. Now, case-based reasoning also falls under machine learning categories, but case-based reasoning is the process of solving new problems based on the solutions to the previous problems. So Heisen and Son used a case-based reasoning model for StarCraft replays to construct states and building sequences. Shad and Co. has applied case-based reasoning to approach the opponent modeling through hierarchical structured models of the opponent's behavior. Now, scouting is a very important factor to partially observable games like StarCraft. But most commercial RTS AIs cheat because they know the entire state space. Now, there's little published research on this topic except from Weber, who used particle models with a linear trajectory update to track the opponent units under fog of war. This produced tactical goals through reactive planning and goal-driven autonomy. Tactics are divided into 2 groups: spatial reasoning and decision making. Spatial reasoning is the most, and in its most common form is terrain analysis, provides structured information about the map. Perkins applied a Voronoi decomposition to detect regions and relevant choke points on a map. Walling is another form of spatial reasoning, and is the act of intentionally placing buildings at the entrance of your base to block the path and prevent opponent's units from getting inside. Now, decision making using machine learning, Sharma has combined case-based reasoning and reinforcement learning to enable the reuse of tactical plan components. Miles has created an IM tree, a tree where each leaf node is an influence map, and each intermediate node is a combination operation, like sum, multiplication. Miles used evolutionary algorithms to learn the IM trees for each strategic decision in the game, involving spatial reasoning by combining a set ASIC influence map. Decision making using game tree search. There are many applications of game tree search in decision making, but most interestingly in this paper would be the greedy portfolio search. This search performs abstraction at the level of action by employing a collection of predefined scripts, using these scripts as the possible actions that the player can execute in the context of game tree search. Reactive control for AI RTS. Now, potential fields and influence maps have been found to be useful techniques for reactive decision controls. Some uses of potential fields in RTS games are obstacle avoidance and opponent fire avoidance. Potential fields have been combined with A-star pathfinding to avoid local traps. Bayesian modeling has been applied to the inverse fusion of the sensory inputs of the units, which subsumes potential fields, allowing for the integration of tactical goals directly in micromanagement. Wender and Watson have used different RL techniques for decentralized micromanagement, while Churchill has presented a variant on the alpha-beta search that deals with simultaneous moves and durative actions, which could handle reactive control. Next, pathfinding, which does fall under the reactive control for AI, is the most common algorithm used is A-star. But the big problem with it is that it uses a ton of CPU time and memory. So an attempted solution to this has been the triangulation reduction A-star that computes polygonal triangulations on a grid-based map. This technique considers the movement of the group instead of the unit. Think of this as flocking behavior. Finally, we have holistic approaches, which technically are just ways to encapsulate the entire AI or the entire game in one single AI algorithm. Now, there isn't much research in this just yet, but there has been some by Darmok, who has attempted to create a system that uses a combination of case-based reasoning and learning from demonstration. Thanks to everyone for listening. If you have any research or questions or interest in any of the research presented here, I will provide the paper below. It was a very good read, and I can't wait to dive deeper into some of this stuff. Thank you.